Hello. So, as Silesh said, I feel like having contributors and end users all together in the same room is really just an expression of this like symbiosis that we all have. And it's really cool to have so many people here today. I think our final tally was like 148 registries or something. So we have a lot of people here today, both from contributor and from end user perspective. Last time we had an Unlocked conference, it was in San Jose. And I gave a talk about atomic slot migration, which we had just launched back in October. And the topic of this talk was making resharding boring. And I wanted to revisit this concept of boring systems. And like as Kawaja said, I have this kind of goal of making Valkey an overall more boring system. But like, I mean boring, and I don't mean uninteresting, and I don't mean unsophisticated. What I really mean is like a system that's overall very understandable, and a system that's easy to operate, and a system that's not driven towards what's the most recent hype, but that's driven towards what makes the system the most operable. So today I wanted to talk about, at large, like how do systems get built that are boring, and how are we making Valkey a more boring system? Before I get into that, I could tell you a little bit about myself. My name is Jacob Murphy. I'm one of the staff engineers at Google Cloud. I work on the memory store team. Memory stores are managed in-memory database team. And I've worked on that team for the last 6 years, working on things like Memcached, Redis, and then most recently working on Valkey. Over the last 2 years, I've had the opportunity to become a contributor to the Valkey project. One of my first contributions to Valkey open source was actually rebranding all of the comments that we had in the Valkey codebase to remove Redis and rename it to Valkey, which was a very impactful change. Since then, I've actually made a lot more impactful changes that you may actually notice in production. Most recently, I led the atomic slot migration project last year, which was, as I mentioned, our attempt at building a new resharding primitive for the Valkey data plane. As a culmination of that effort, I most recently was added to the steering committee of Valkey, where I've served as a maintainer of the project for about the last 6 months. Before I get into boring systems, I wanted to talk about an anecdote, which was the worst page that I ever had. And coincidentally, it actually has to do with slot migration, which is part of the reason I was kind of radicalized to take on this problem. But in this case, what made the page so bad wasn't actually necessarily the content of the page or the impact of the page. It was really just when I got the page. In this case, I was actually planning to hand my pager over to someone else in about an hour. And I had a wedding to get to in Spokane. And I'm based out of Seattle, so it was about a 5-hour drive away. And my plan was I'll hand over the pager. I'll drive for 5 hours. I'll go to my wedding. And then the next day, I'll resume being on call. Except my plan was foiled by the legacy slot migration code that we had before. We had a cluster that went to go scale out to meet some additional throughput requirements. And it hit a stuck, it got stuck during the scale out. And what happened was there was actually a very large key, and the large key would not get migrated through with the old legacy slot migration code. And what was even worse is that the old slot migration didn't support anything like rollback. You were actually forced to roll forward in order to finish the migration. And getting stuck into a situation like this meant that I had to figure out, by whatever means necessary, we could get this large key transferred from the old node to the new node. And I had to dive into all of the configurations that I could adjust in order to make this transfer happen. It ended up taking about 3 hours to fix. And as a result of that, I actually was not able to drive over the I-90 pass in time. And I ended up booking an urgent flight to get to Spokane after this. So not only was there some extended customer impact, I actually was personally financially impacted by this page. And it was a very stressful experience. And I think this is a great example of Murphy's Law, which we've all heard before. And it's basically, anything that can go wrong will go wrong. And I think people, think of it more as like a joke but it actually comes from an engineering background. The guy that created it was an aerospace engineer, and he was looking at, they were testing aerospace components, and he said, anything that can go wrong will go wrong. As a matter of like availability, any component in the system can go wrong, will eventually go wrong. And it applies very well to our jobs as software engineers because it basically says that time and scale will reveal all potential outages in your code base. And as a kind of an ancillary law of Murphy's Law, you don't get to choose when these outages happen. And so that gets me to what I've been calling the 3 a.m. test, which is essentially at 3 a.m. or whatever metaphorical 3 a.m. you have, which is just like, what is the worst time that you could get paged? Will you be able to understand your system quick enough to be able to debug an issue that comes up? Or are the complexities going to get in the way and you're going to need to debug things in production? And I think this is where you will be very thankful if you built a boring system because it becomes very understandable and very quick to debug and to roll back. But in the case of slot migration, we were actively failing this 3 a.m. test pretty frequently. So on that topic, I have a couple things I wanted to say about why systems tend to fail at 3 a.m. And I think one of the big reasons that systems do fail at 3 a.m. is bimodalities. And a bimodality is actually like a statistical term for a certain probability distribution where you have two distinct peaks. And I think that you see this happen with all kinds of service health indicators, whether it's latency or availability. But these two distinct peaks usually come from some kind of mode switch that's happening in your system. And I kind of think of it as you have like a sunny day and you have a rainy day. And the sunny day scenario is the one that you're spending like 99% of your service's time in. But that 1% situation is where you usually end up getting paged. And complex systems tend to alternate between modes. And these mode switches are complex and they drastically change the service's characteristics. In the case of slot migration, I'm showing here a model of request latency. And you could see that during no migration, you would see one latency distribution. And then during the slot migration, you would see a different latency distribution that was worse. And this can kind of come as a shock to the system when these mode switches do happen because your profile of your system changes significantly. And I can get in later as to why this was happening with slot migration and what we did about it. But another problem, and this can come as a result of this bimodality or mode switch, is metastable failures. And this is where you have some kind of load spike or capacity reduction in your system that causes the error rate to increase. And as a result of the error rate, you actually end up with a metastable failure, which is a fancy term for a feedback loop. Effectively, you have client retries that create a storm because of all the errors. And even after that capacity reduction or that load spike is resolved, you can end up with continued unavailability because the baseline plus the retries are still in excess of your capacity. I think we see this a lot in Valkey in the context of clients, and it's another reason why it's so important that we invest a lot in our clients and all of the complex retry and timeout logic that goes into those. But a boring system overall needs to aggressively soften these spikes and have graceful degradation. And finally, this is the one that really bit me with slot migration, is the complex systems tend to have these irreversibilities. So all of our systems are state machines at the end of the day, and those state changes are often when our systems fail. In the case of slot migration, you go through kind of two state changes. You first are moving something from the source into a migrating state, and then migrating all the data over, and then you're going from the migrating state into owned by the target node. The problem here was that once you started the migration, there was no state change that you can make to reverse that migration without completing it. And this forced you into a unidirectional mode of the state machine, and that meant that operator, that was me, had to go and figure out exactly how I can go from migrating to target instead of just going back and rolling back the change. And you see this pattern come up not just with resharding like we saw here, but also with complex migrations where you might be moving one of your components from one system to another, schema changes, or even version upgrades, right? Like if you're upgrading from Valkey 8 to 9, sometimes that can be a unidirectional state change, and those can create complexity. And so I think with all of these different things, it really goes to show you that it's important to prioritize the boring work. I think every feature that we launch on day one comes with a lot of complexity. And those complexities are maybe understood, but oftentimes you don't know what complexities exist until you run that thing in production. Boringness is not something that is innate to any given system. It's something that's derived over a long time. And I kind of think of this as you have this boring asymptote that you approach. From day one, you launch with a lot of complexity, and over time you polish, you cover all the edge cases, you find out what configs need to be tweaked so that you don't enter those metastable failures, and overall the system becomes more boring over time. In the case of slot migration, our boring asymptote that we were approaching with the old slot migration was actually quite complex. And so sometimes you do need to pivot and change designs to approach a more boring future. And I think that's what we did with slot migration. And on the topic of approaching boring, I really do think that this boringness is not accidental when it comes to open source projects. I think it's actually a manifestation of how open source works. If you look at some of the most, what I would call boring projects out there in this kind of endearing way, you have things like Postgres and SQLite, ext4. These are very hardened systems that all come in, they're all in the open source, and they all have some level of open governance. And because of that, I tend to think that this decentralization, this open governance, really optimizes for boring outcomes. You have, in the case of Valkey, these companies like Amazon, Google, you have Oracle, Ericsson, you have independents, you have people that are just hobbyists, people that are doing side projects that are using Valkey. Everyone's coming together in the community, and they're all coming from different perspectives. They're all coming from different production environments, different levels of scale. They've seen different failures. And so no single party is able to kind of rule and just make decisions on behalf of the whole project. In order to get like the median group to agree, you need to find the common problems that we're all solving. And I think these tend to be the boring things. So we end up investing in things like memory efficiency, improving failover operations, improving resharding, like I said. And I think it comes through if you look at some of the core ways that Valkey operates. I think when we first launched, we had options that we could have done to try to generate more hype for Valkey overall. We initially launched, we spent a lot of time focusing meticulously on wire compatibility with Redis. We even added a mode in our server where you can enable something we called extended compatibility. And extended compatibility meant that even error messages that previously had returned Redis, we kept that if you turned on the extended compatibility. So we were incredibly thorough in thinking about wire compatibility. But like as an alternative, if we wanted to generate the most hype, we could have completely disregarded the existing protocol and started making changes left and right. And we could have written a bunch of blog posts about what we were doing and how bad the old system used to be, right? But that's not exactly what our users wanted, right? When we went out to the open source, everyone just wanted to lift and shift over. They didn't want this massive disruption. They wanted stable incremental progress. And that also comes on the side of threading. In Valkey 8, we redid a lot of the threading. And in 9.1, we're going to do it again. But we're always applying our multi-threading intentionally. I think a lot of other projects have tried before at really deeply multi-threading Redis. But it keeps coming back to this simple single-thread execution loop. And I think there's something very simple and boring about that tends to create this very stable P99 latency. You don't have to think about mutex contention. You don't have to think about MVCC and memory bloat that happens from keeping multiple versions around. Everything is single-threaded and very boring. And in all the other initiatives that we're doing, like vector search, these are problems that can definitely be used for AI, but we're not trying to force AI into anything. We're definitely focusing on the common problems with search that people are facing, and not over-indexing on the current hype bubble. And that's just a manifestation of how decentralization works. Just to drive the point home, I think you can kind of think about two different projects, one centralized, one decentralized. You fill in the blanks. And on one side, you're going to find a project that, in all likelihood, is going to be able to move faster because it's single vendor. There's no decision overhead. Everyone can just do what they want. But you're going to find a roadmap that's going to, at the end of the day, answer to business strategy, quarterly goals, and competitive positioning. On the other hand, your decentralized project, it's going to move more deliberately. The decisions may make more time, but the decisions that come out of it are going to be boring, and they're going to incrementally improve the product and not over-index on what the current investments that they're going to get are coming from. And ultimately, it's going to lead to an operations-first model where, on the other hand, you tend to find projects going into a sales-first model. On that topic, I wanted to talk about hype and how easy it can be to kind of build hype. And as part of that, I actually worked on a simple project here. It's basically a shell of Valkey that I had an AI vibe code, and I called it benchmark KV. And the goal with this was I gave it a white box view of Valkey benchmarks tool, and I said, build whatever you want, just make it Valkey compatible, and make it as fast as possible. And the benchmarks I was able to get out of this looked very impressive at first. I was able to get 2.8 million QPS on sets compared to Valkey's 1 million QPS. So something that I built in 7 minutes was able to out-benchmark Valkey. So obviously, it must be very good, right? But I think you have to be hesitant about this thing we call like benchmarking. If you look at the details of how benchmarks are done, you're going to find that they don't really have any real workload representation. In this case, it was using 100 depth on the pipelining. And if you don't know, pipelining is this concept of continuing to send requests on a TCP connection before getting a response. And I think that a lot of workloads can heavily pipeline and heavily utilize this. But a lot of other workloads are unable to. They have to do unary request response just by nature of how the workload works. And if you reduce the pipelining down, the benchmark KV performance gain is very minimal. It only gets like about 4% extra performance. And then this is all coming at the cost of a different latency distribution that you see with this AI vibe-coded Valkey. I only shared the P50 latency on the previous slide here, which made it look really good. But if you looked at the full latency distribution, you would find that the tail latency is actually much worse. And it has to do with how the threading was built on this AI vibe-coded project. It used a mutex pool, and because of mutexes, you end up with some amount of mutex contention. That mutex contention is going to be felt at your P99 and P100 latency. And in this case, it ended up with about 50% worse on those tails. And then finally, the Valkey benchmark tool, although we build it, it's in the core database, or the core code base. It doesn't actually represent any real workload. It's a small key space in this case. It's configurable, but the AI chose a specific, I think, 100,000 keys. They're all the same size. In this case, it was like about 1 kilobyte. And it's all a uniform load generation. So each key is uniformly accessed just as frequently as each other one. But if you look at real workloads, they never follow this uniform access pattern. They're always Gaussian or power law distribution. And in those cases, you're going to see even worse mutex contention. And I think finally, we talked about bimodalities and all these mode switches and all those things. I think your benchmark is usually only ever capturing your happy case. And you have to think about these rainy day scenarios more often than you have to think about the sunny day scenarios when you're building systems. And benchmarks never capture any of that. On that topic, I wanted to talk about some of the work that we're doing in Valkey that is this hard, boring work to kind of prove we're doing the legwork here. Obviously, I wanted to start with the project I led, Atomic Slot Migration. So I mentioned before, when you were running the legacy slot migration, you had a few problems. One of them was that your request latency was impacted by the fact that your client had to go to 2 different nodes to figure out who owned what key. And this meant that during your migrations, you would see different latency profiles than when migrations weren't running, creating this bimodality, potentially even creating metastable failures. And the other problem here was that we would move things atomically at the key level, from the old node to the new node. And by needing to move things atomically at a key level, you were unable to do a level of pipelining. Sorry, did you have a hand? Oh, what's a slot? Good question. It's a bucket for consistent hashing. So the keys get consistently hashed into buckets. Each bucket, we call it a slot. There's just a fixed number of slots. Thanks for clarifying that. So in order to reshard data, we would move slots between the old nodes and the new nodes. There was a fixed number of slots, and you would redistribute them over the new number of nodes. But if you were forced to move everything atomically at the key level, you ended up getting blocked on these large keys because there was no way to atomically apply that without exposing any intermediary state, without one needing to buffer a large key in memory, which could lead to problems, and two, you needed to replay that key on the main thread, which could lead to seconds of latency, potentially minutes of latency that could cause failovers. So with atomic slot migration, we flipped it on its head and we decided really all you needed to do here was copy over the whole entire slot from the old node to the new node. And we could use like a snapshotting primitive. And as part of this, we take a snapshot and then we send over like a change data capture of all changes that happened since we took the snapshot. And at some point, the destination is caught up completely and we're able to cut over and at that point, clean up the old slot. This makes it completely cancelable because you can always just delete the copy that was on the source or delete the copy that's on the destination and go back to the beginning, which would have made my experience much better when I got paged. The other nice thing about this is because we're no longer batching keys, we're sending a full snapshot of the slot. It's up to 9x faster. You're able to heavily pipeline this workload, and you no longer have to deal with your round trip time being in between you and your migration. Another really good thing that Valkey's been working on is memory efficiency. I think this is a really underrated feature that we've worked on because although you don't see this come up on benchmarks, you do see this come up in your actual wallet, right? Because most people are constrained on the cache hit ratio. They need more memory in order to store more keys. And by reducing the amount of memory per key, we're able to just give people more money back to their wallet. So in Valkey 8, we did something. We looked at each key and we realized we had 3 pointers that we could actually get rid of. And 3 pointers is 24 bytes on the 64-bit architecture. And you would think 3 pointers, 24 bytes a key, that's not really that much. But when you look at a lot of workloads, they tend to cache very small keys. And these small keys in aggregate add up to lots of memory. And so even just 24 bytes a key, if you have 1 billion keys in your cluster, right, that's 24 gigabytes of memory. So it ends up adding up to a lot of memory. In Valkey 8.1, we continued on this thread and we actually redid the whole entire hash table in the main dictionary. And we used something called the Swiss table, which came out of actually Google's research. And by doing this, we were able to save an additional 20 to 30 bytes a key. So now we're up to maybe 54 bytes a key in savings. And also with this new Swiss table, we were able to store existing data structures like sets, hashes, sorted sets. Some of these are encoded behind the scenes as hash maps inside of the database. So by using this new hash table, we were able to save lots of memory for people that heavily use those. So if you had 50 million entries in a sorted set, you were able to save now over 1 gigabyte. So again, like it's not something you'll see in the benchmarks, but it is something that actually impacts people at the end of the day. Finally, I have a preview, and Jim is going to talk more about this later. But in 10.0, we're looking at launching this feature called forkless save. And the problem here was that when we used to snapshot in Valkey, we would always use a child process to essentially capture the state of memory at some point in time. And then we would transfer we take this child process that had a view of memory from some point in time, and it would transfer over all the contents to the target node. Or to a snapshot file if you were taking a disk-based snapshot. And it turns out that creating child processes, although a very cheap way to get an in-memory snapshot, over time creates a lot of copy on write memory. So what happens is the kernel, every time you dirty one of these pages that's shared between a child and parent process, it needs to make a copy. And over time, the longer that snapshot runs, the more memory you use. So I have a visualization here, like if you're using your baseline 1x memory, you start a snapshot, you're going to gradually see the memory growth grow to up to 2x memory with the child-based approach. Additionally, you have another problem, which is that the fork syscall has a very high latency, especially if you have a lot of memory. The Linux kernel will pause your process completely in order to do a lot of memory accounting to create this child process. If you have a lot of pages of memory, it can take up to seconds. And so we've been looking at this problem, and Amazon actually has a solution that they've been running in-house for a while that they're looking to open source, and it's called forkless save. And the way this works is that instead of creating a child process, we just create a thread. And we do a lot of accounting inside of Valkey to make sure that we're able to either create a consistent snapshot from the point in time that you asked for the snapshot, or an eventually consistent snapshot for the purpose of replication. So there's no latency from the fork syscall anymore, and you're able to get rid of this 2x memory bloat. And essentially, we're pulling in a lot of the logic that the kernel is doing and tuning it specifically for Valkey. And specifically, it's able to reduce a lot of this bimodality that used to happen where either you were having a snapshot or not. And additionally, there was a lot of metastable failures that would come here where replication would get into a loop, and then it would continuously retry, and it could actually take the primary offline. So that's all the ways that Valkey is working on making it a much more boring system. And hopefully this will allow the users of Valkey to sleep better at night. And I just want to leave one last thought, which is that just like I talked about with benchmarks, throughput maybe isn't the best benchmark, but I think the hours of sleep you get a night is much better. Anyways, thank you, everyone.